Hello, welcome to the Penguin Prof channel. Today I want to get started on a chemistry concept series by popular demand. We're going to be talking about elements, atoms, really why it's all about the electrons, and some Lewis dot structures, which in my opinion may be the key to happiness. When we get started here, we're really talking about what stuff is made of, and stuff is made of matter. From here, you can really kind of go off a cliff in terms of how far you want to go into this. This is really the realm of physics. So I just want to say from the outset that this is a highly abbreviated version of an understanding of what the stuff is in the universe. Matter is made of elements. Elements are pure chemical substances that you can't break down into anything else. Now, we organize elements in this amazing table called the periodic table of the elements. It's really amazingly organized, and I'm just going to say it. It's beautiful. Okay, how much of a geek am I to say that? But it really is, because if you understand how this table is organized, this is tremendously powerful. Notice I didn't say if you memorize it. I do not have my students memorize any part of this table. That's what it's there for. That's why you can look it up. But you have to understand how to use it and what it means. In terms of elements in the universe, the vast majority of them are the two smallest elements, hydrogen and helium. On our planet, in the Earth's crust by weight, we've got oxygen, silicon, and aluminum. If you take the Earth as a whole, not just the crust, by weight, the most abundant element is iron. In terms of biology, only 25 elements are essential for life. And of those 25, only 4 make up the vast majority of most living things, including penguins. So if you're wondering, well, what are we made of? You'll be thrilled to know that you can actually buy a shirt with human ingredients on it. Oh my gosh, I love these geeky gifts. I don't know what that barcode is at the bottom. But anyway, so here's a nicer view, table of the elements of the human body. And again, you can see that over 96% of humans are made of oxygen, carbon, hydrogen, and nitrogen. So if you go back to the periodic table, and it is kind of overwhelming, I admit, but you remove all of the elements that are not found in humans, it's really not too bad at all. This looks somewhat manageable, right? Understanding the periodic table also allows you to understand all these stupid geeky gifts, like this bacon shirt, which I don't know, I was just in a weird mood. Okay, so the smallest unit of an element, which retains all of the properties of that element, is called an atom. That word comes from the Greek, a term which means not to be divisible, meaning you can't cut it up into smaller pieces and still retain the properties of the element. We can actually see atoms today. This is a really cool transmission electron micrograph done by the physicists at UC Berkeley. The red arrows are hydrogen. That black arrow is a carbon atom shown on the surface of graphene. Now, in your textbook, you will see atoms drawn like this. Electron clouds, the shell or Bohr model. And I got to be honest with you, this is just not true. Atoms do not look like this. We use these drawings because they represent sort of an easier way for us to talk about them, but this is not what atoms really look like. Atoms are really hard for us to wrap our brains around because they are unbelievably small. That black bar right here at the bottom represents 1 angstrom, or 100,000 femtometers. So an angstrom is 10 to the minus 10th meter. And the vast majority of the atom is actually empty space. So over 99% of the mass of the atom is concentrated at the center in the nucleus. And the rest of it, where the electrons are, the orbitals, are just hugely spread out. And it is really difficult for us to really draw and think about what atoms really look like. So I have a couple of analogies for you, of course. One is an analogy of scale, and this is a soccer field. And if you take the nucleus to be the size of the soccer ball, then an electron could be a fly buzzing around the spectators. And most of the stadium represents the space between the atomic nucleus and the electron. So most of the atom is empty space. Now, this analogy is not really accurate either because it shows the electron as a particle, as a fly. And actually, that's not true. One of the best analogies that a chemist gave me for this is with cotton candy. And he said, okay, where's the sugar? Well, the sugar's kind of everywhere. I mean, the whole cotton candy is made of sugar. That's kind of the same idea with these electrons. So the orbital itself really is the electron, but that's really hard to draw and describe. So what I always say is, strive for understanding, strive for the real truth, but we, like all of your textbooks and basically everybody else, we're going to use these models and drawings. We're going to draw the little electron as like a ball or a bead so that we can keep track of everything. Okay, but realize that that's not really the truth. So getting back to the atoms and the periodic table, there's a couple of numbers that we need to concern ourselves with. One is the atomic number, and that's just the number of protons that an element has. And I'm picking carbon here as an example. The atomic number for carbon is 6. What that means is that carbon has 6 protons. That number does not change. It's kind of like your calling card. So if you add a proton to carbon, it's not carbon anymore. So now your atomic number would be 7, and now you're nitrogen. So the atomic number does not change. The mass number, or what we call the atomic weight, that's the number of protons plus the number of neutrons. The first thing that you notice is that these numbers are decimals. So maybe you're wondering, well, are there fractional protons and fractional neutrons? And, what's up with that? Well, what we're really getting at here is the mass number is actually an average. So the number of protons does not change, but the number of neutrons can change. So if we look at carbon in the universe, there are different numbers of neutrons in various carbon atoms that you could find. We call these isotopes. Most carbons in the universe have 6 neutrons. And of course, the number of protons doesn't change. So 6 plus 6 is 12. So the vast majority of carbons that you would find have the mass number of 12. You will also find, though, some carbon atoms with an extra neutron. And if you add 6 plus 7, that gives you the mass number of 13. Some atoms have 2 extra neutrons, 2 more than the normal number, and the mass number here is 14. This is probably the one that you're most familiar with. Carbon-14 is what we use for dating. Not dating, will you go out with me, but dating, how old is that tree? We use isotopes for all kinds of purposes, actually, in medicine as well as radioactive dating, because they decay at a constant rate. So if you look at the decay rate of carbon-14, this is what it means. So we have times 0, some amount of carbon-14 that's present. After one half-life, which for carbon-14 is about 5,000 years, after one half-life, you have half that amount still remaining. After 2 half-lives, you have half of that half. And after 3 half-lives, you got another half. So it's not like after 2 half-lives, it's all gone. That's a big misconception. So what you should notice is this exponential rate of decay. And this rate is constant. So that's why we can use isotopes to date living tissue, to date rocks, and things like that. But enough about the nucleus. Chemistry is really all about electrons. So we're going to spend the rest of this video talking about them. Now, atoms like to be stable. And in order to become stable, sometimes they have to play with other atoms. In this way, they're kind of like people. But you might ask the question, does everybody need to play with others in order to be happy? Humans are social creatures, so most of us do, but there are actually individuals that don't. And the same thing is true in the periodic table. We have to the far right the noble gases. Noble gases, so named because, like nobility, they do not mix with the commoners. And in this video, we're going to explore why. Why don't they form bonds with other atoms? Everybody else on the table, they form bonds, but not the noble gases. You got to understand the electrons in order to understand why. So, electrons fill around the nucleus from the inside out. And what I mean by that is as you look at different atoms, and different atoms have different numbers of electrons, they will fill around those nuclei from the inside out, just like water fills in a glass. When you fill a glass with water, it fills from the bottom up. Okay, you can't do it any other way. If you can, I'd like to see that. Shell number 1 is going to hold 2 electrons. Shells 2 and 3 are going to hold 8. Yes, For you chemists, I am oversimplifying this. When you go on and take more general chemistry, you will see that the electron configurations are a little more complicated than that, but for the purposes of general biology, what I'm giving you should get you through most of the problems that you're going to come in contact with. I just got to say, don't get your heart rates up when you see stuff like this. Even at first glance, you notice that there is a pattern. So this is manageable. But we're not going to go into that in this video. We're going to focus on happiness. What you got to remember is that atoms are happy when their outer shell is full of electrons. The outer shell turns out to be so important, we actually give it a name. We call it the valence shell. So we're going to talk about how they get to be happy right now. As we go through this, we're going to see that carbon is not happy by itself, whereas neon is. We're going to see why. My analogy for this is a stadium in the round. So a stadium with a stage inside and spectators all the way around. And of course, we're going to have penguins in there too. So we're going to have a rule and a goal. The rule is we're going to sell tickets closest to the stage first. The goal is we want to make each shell around the stage full of spectators. Now, in our little theater, it's going to be a very little theater. The first shell is only going to have 2 seats in it. The second shell is going to have 8 seats, and the third shell is also going to have 8 seats. So just go with me on this, okay? It's a small, intimate theater. So here are our seats. We're going to look at different scenarios and see what it looks like. So here's the first scenario. We sell 1 ticket. So we're going to satisfy the rule. The tickets that we sell are going to be closest to the stage. The goal is not met, though, so that's not so happy. We have 1 empty seat in the first ring, and this is actually hydrogen. Another scenario, we sell 2 tickets. So the rule is they're going to be the ones closest to the stage, so that's all good, and we actually met the goal. The shell is full. So that's a really happy, stable scenario, and this is actually the element helium. What if we sell 7 tickets? So notice the rule, we're selling the tickets closest to the stage first, but you notice now that we have 3 empty seats in that second shell. So this is nitrogen. This explains why nitrogen would want to form bonds to try and fill those empty seats. What if we sell 10 tickets, though? Now you notice that the first 2 shells are full. This is a very stable configuration, and this is actually the noble gas, neon. What about 13 tickets? So now we're moving into that third shell. We're always filling from the inside out, but now that third shell has only 3 occupied seats and 5 empty ones. So that's not so happy, and that is the element aluminum. In our last example, we have 18 seats, and you notice we have all 3 shells full. This is a very stable configuration. This is the noble gas, argon. So maybe you've noticed that it seems to be about the valence shell. If the valence shell is so important, why don't we just focus on that? I mean, who cares what the core of the beast looks like? Let's just look at the outer shell, since that's what's going to determine how happy an atom is. If you're thinking that, that's awesome. You're not alone, because some other really smart people have thought exactly the same thing, like Dr. Gilbert Lewis, who is a physical chemist. He spent most of his career at UC Berkeley. And he did exactly that. He said we should draw an elemental symbol, and then we're going to draw the valence shell electrons around it. And I always tell my students, if you keep track of the valence electrons, you're going to be happy. So let's see how this works. We're going to look at carbon. The most important part in terms of carbon's reactivity is the valence shell. So let's just get rid of everything else. And we're going to draw only the electrons in the valence shell around carbon. That's the most important part. So carbon has the atomic number 6. And now you know that 2 of those electrons are in the first shell, leaving 4 for the valence shell. Now, I just want to remind you, those penguins represented electrons. But for heaven's sakes, don't draw penguins in your Lewis dot structures. You're going to get kicked out of class. So what we do is we draw literally dots around the element to represent the valence electrons. And ta-da! That is the Lewis dot structure for carbon. How easy is that? So let's look at nitrogen. So to draw the Lewis dot structure for nitrogen, all you do is you draw the symbol for nitrogen, and then you go around it and draw the valence electrons, starting at the top. Now how you draw these varies. This is the way that I was taught. Starting at the top and going around, nitrogen looks like that. So let's look at aluminum. So here's the symbol for aluminum. Aluminum has 3 electrons in its valence shell, so you draw them around going 1, 2, 3. That's aluminum. So finally, let's do argon. Argon has a full valence shell, so we're going to draw 1, 2, 3, 4, 5, 6, 7, 8. A full valence shell for argon, and it's as simple as that. So check this out. If you look down the column of all the noble gases and you draw the Lewis dot structures for each one, you will find that they all look the same because all of them have full valence shells. And this explains why all the noble gases are happy as they are and they don't form bonds with other atoms. Because if the goal is to have a full valence shell and you already have one, you don't need to play with others. The only thing that might confuse you is helium, and what you have to remember is that helium is very small, atomic number 2, so it has only 2 electrons. And so you have to remember that that first shell is in fact full with 2, whereas everybody else going down this group, they will all have an outer shell full with 8. So let's practice. When you practice drawing the Lewis structures, all you need without the penguins, is a periodic table. So lithium, atomic number 3, is going to have 2 electrons in the first shell, leaving you 1 in the second shell. So when you draw the Lewis dot structure, that's it. 1 electron in the valence shell. For oxygen, you've got 2 electrons in the first shell, 6 in the second, for a total of 8. So you draw your oxygen with 1, 2, 3, 4, 5, 6 electrons in the valence shell. That's your Lewis dot structure for oxygen. Sodium has 2 in the first shell, 8 in the second, 1 in the third, for a total of 11. Sodium is drawn just like that. So it's really not too bad. And even though most biology instructors don't really show you Lewis dot structures, you're going to have to do it in chemistry anyway. And truthfully, if you understand Lewis dot structures, everything else is going to make a lot more sense. So here are the first 20 elements and the Lewis dot structures for each. And what you notice is that as you go down the vertical columns, which we call groups, they all have the same Lewis dot structures. And that explains why they have the same chemical reactivity and why they'll form the same kind of bond. Isn't that cool? How powerful is that? So understanding Lewis dot structures is going to make predicting atomic interactions so much easier. And you're going to be able to predict what's going to happen when, for example, 2 hydrogen atoms get together. Because unless you're a noble gas, you're going to have to play with others in order to become happy. And that's what atomic bonding is. And that's why 2 hydrogens get together to form H2, hydrogen gas. So they're both going to share their lone electron so that each one can have a stable, full shell. As always, I hope this was helpful. Thank you so much for visiting the Penguin Prof channel. Please support by clicking like, comment, share, and subscribe. And join us on Facebook. Follow on Twitter. As always, good luck.